nice seeing you again, Adam Scotch, leader of the printed electronics gang at Brewer Science. And Adam, feel free to start screen sharing.
Very good. Well, thank you very much, Christoph. I appreciate it. I'll be sharing with you a very application-specific topic on printed arrays for on-demand water quality monitoring. So it's a little bit different from the talks we've seen so far because we're now looking at a real full-scale application rather than a process of how we got there. So first, a little bit about Brewer Science. Brewer Science has been around for over 40 years. It's primarily focused on the material science world, supporting mainly the semiconductor industry in advanced lithography of semiconductor wafers, as well as semiconductor packaging solutions. I actually come from the smaller third business called Smart Devices, where we sort of enable the materials that we have developed over the course of a number of years to put them into actual real sensor devices and for monitoring applications. So today I'm going to be talking to you about our latest developments in our water sensor and water monitoring applications. So primarily, why are we doing this? Effectively, current ways of monitoring the water in our environment is slow and cumbersome. There is no cost-effective inline monitoring solution that exists to be able to measure in the parts per billion range on the market. So instead, what happens is water samples are generally collected manually, as shown here in the picture, and that's sent then to a certified laboratory. Often, the samples need to be adjusted with buffers and filters and so forth, and have very specific procedures required. So lab testing on a regular basis can be very expensive, and it also provides only a single snapshot in time. I mean, there are some benchtop solutions, like one pictured here, to be able to measure specific analytes, but again, no inline monitoring solution. So our aim really is to develop a sensor system that could be used for multiple environments. So our holy grail is what we're looking for right now. And long term is be able to monitor our lakes, rivers, and streams because it's our most precious natural resource, but also to be able to monitor our water quality in waste treatment plants or water treatment plants, monitoring clean water at the tap or in buildings, as well as in healthcare or industrial applications. Currently, I show a picture of our sensor here. It's a flow cell based sensor, which is shown roughly around 4 inches in length. The current sensor that we have right now is an array that can measure temperature and conductivity, as well as lead, pH, and nitrate. Again, really what our aim is over the long term is to be able to develop low-cost sensors to provide distributed monitoring of our water systems or here on Earth, and create a map that looks something like this, a sort of heat map of what's the quality of our water in our area. This is an example. This is just an example picture shown from a satellite image, actually, which monitors sedimentation. But this is sort of the concept of what we're really aiming for in the long term. So here's the details of our sensing array. This array is a double-sided substrate. We have a reference electrode, as well as we can put an array of any sensors on here. Since it's all in a line and we have water flowing across these from left to right, we can put as few as 1 or 2 electrodes here, or 50 or 100 if we want. And really, we show here a nitrate sensor, lead, pH sensor, along with a temperature and ionic conductivity as a measurement. These are what's really specific here for us is that each one of these electrodes really depends on this membrane, which gets deposited on top of the electrode. And this membrane is very specific. It's ion selective, and this is the material that we develop in-house for our needs to be able to detect lead, nitrate, pH, and any other analyte that we are working on. So the front side of the board is